isn't the best place to find a lover, so the bar is where I go. Me and my friends at the table doing shots, drinking fast, and then we talk slow. Come over and start a conversation with just me, and trust me, I'll give it a chance. I put my hand, stop, but then the man on the jukebox, and then we start to dance. And I'm singing like, boy, you know I want your love. Your love was handmade for somebody like me. Come on now, follow my lead. I may be crazy, don't mind me, say girl, let's not talk too much. Grab on my waist and put that body on me. Come on now, follow my lead. Come on now, follow my lead. I'm in love with the shape of you. We push and pull like a magnet do. Although my heart is falling too. I'm in love with your body. Last
Tercer llamado. Vamos a dar inicio al evento. Tercer llamado. Vamos a dar inicio al evento. Bienvenidos al auditorio Mario Lacerna. Al ingresar al auditorio, ubique las salidas de emergencia señalizadas con luz verde. En caso de emergencia, conserve la calma y evacúe con precaución. Le solicitamos el favor de apagar sus teléfonos celulares y les informamos que está prohibido consumir alimentos y bebidas en el auditorio. Gracias.
Hola, buenas tardes a todos, todas. Qué bueno ver tanto interés en un tema que tiene que ver con ciencia y específicamente con física. No todos los días tenemos la visita de un premio Nobel a la universidad, entonces es un enorme honor poder darles la bienvenida a este evento. I'm going to switch to English so that our invited speaker can follow, but hopefully this is going to work for everybody here. So hi everybody, my name is Daniel Cadena. I'm the Dean of the School of Sciences here at Universidad de los Andes, and I wanted to welcome everyone to this event and say hi to everybody that is connected via streaming. Thanks for tuning in. I wanted to start by saying that at the Universidad de los Andes we have been engaged in two important discussions for which today's event appears especially relevant. First, our current institutional development plan for 2021 to 2025 outlines a dream of the sort of institution we want to be, which states that the university should have greater impact on a diversity of audiences in academia and society. I should say that this has caused tension among some of our faculty who have interpreted this dream to mean that we want to move away from basic science and research to initiatives that have more immediate utility. This, of course, is not the case, for without fundamental science, there can be no such thing as applied science. And the limits between what we call basic or fundamental science and applied science are totally blurred. And an institution cannot sort of commit to one kind of science without giving attention to the other. But the question, of course, is how we make all our science, call it fundamental or applied, at all levels to have more impact. The second related topic that the university has been engaged in is that we're trying to contribute to public debate regarding the scientific policy that Colombia should develop about the sort of science that our country needs. So in these discussions, it has become apparent that countries like ours should perhaps prioritize at least some of its resources to solve pressing problems related to issues such as food security, sustainable development, or adaptation to climate change. In that sense, it appears that investment in science oriented by top-down missions would make some sense. This, however, does not mean that there's no room for science oriented by curiosity, by the bottom-up view in which the state should also support researchers who want to study what they're most interested in. So I think that today's event is going to give us light for those two discussions. What's going on here at the university, and we're trying to do as a university, trying to contribute to the broader discussion about public policy regarding science in the country. And today's talk, which is termed the usefulness of useless knowledge, I think is going to speak to that to a great extent. So in the way of introduction, really our invited speaker today needs no introduction, but I'm just going to say a few words about Dr. Serge Haroche. He was born to a Jewish family in Casablanca, Morocco. His mother, whose family had Russian roots, was a teacher, and his father was a lawyer. At age 12, Dr. Haroche moved to France, and since moving to Paris, he has worked at several institutions, like the École Normale Supérieure, the National Centers for Scientific Research, the École Polytechnique, and the Collège de France, where he's currently employed. He has also spent periods of time working at Stanford, Harvard, and Yale universities in the US. In the 1980s, Dr. Haroche designed ingenious experiments to study quantum phenomena when matter and light interact. As you probably all know, he received the Nobel Prize in Physics in 2012 for groundbreaking experimental methods that enable measuring the manipulation of individual quantum systems. With no further ado, I want to welcome Dr. Serge Haroche. Thank you very much for being at our university. I know it has been a very busy past 10 days for you and a very busy agenda today, but we're very happy to have you here and welcome and thanks for sharing with us.
So thank you very much for your kind introduction. I think your introduction addressed most of the issues I will be talking about in this talk. I will be talking about, of course, about the connection between basic and applied science, and about, as I said in the title, what is the usefulness of useless knowledge. This is a question which is very important because it raises the issue of how much money should be devoted to curiosity-driven research as opposed to the money which is being, and the efforts which are being spent for applied inventions. And of course, as you said, the boundaries between these two aspects of the scientific research are blurred, and in fact, they are the two sides of the same coin. But instead of making very general remarks, I would like to describe this on a very specific example, which is quantum physics, the kind of useful research which came from seemingly useless basic research in this field. So I will start. I will start with, of course, this basic question: why are we doing scientific research? And there are, of course, two answers to this question. One is just to say that we want to satisfy our curiosity. We want to understand how the world works around us, and this is what the Anglo-Saxons call blue sky research. For example, if you ask the question, why is the sky blue? To get the answer, you need to understand how light is being scattered by the molecules in the atmosphere, and this is basic science. And at first sight, you might think that it has no use, but the instruments that we have developed to study the blueness of the sky have been very useful for a wide range of practical applications. The second answer that we give to this question is, of course, that we do science to invent useful and marketable devices, and this is applied research. And of course, governments and private companies very often favor short-term usefulness and consider curiosity-driven research as a kind of luxury, especially in a time where money is scarce. So what I would like to illustrate, to show in this discussion, in this talk, is that this is a really wrong way to state this problem. And I would like to show in a specific example that this is short-sighted, and that blue sky research and technology are the two sides of the same coin, and they cannot be separated. And in order to illustrate that, I will start by trying to make a very general panorama of what we have learned from basic science about light and matter over the last 3 or 4 centuries. But I have to confess first that the title I gave to my talk is not original. In fact, I borrowed it from a book, or rather an article which had been written by Abraham Flexner, who was the founder of the Princeton Institute for Advanced Studies back in the 30s. Flexner was a man who understood the importance of basic science, and in fact he gathered in Princeton in the 1930s people like Einstein, von Neumann, Gödel, Oppenheimer, and all people working also in humanities. And he understood that basic science was absolutely necessary if you want to have applied science flowering. And of course, he is not the only one to have stated that. I found also this very interesting statement made by Henrik Casimir, which I will present you here. Casimir was a basic science physicist, one of the founders of quantum physics back in the 30s. He is a man who discovered the vacuum in quantum physics and the importance of the vacuum to understand deeply what quantum physics is about. And he was also interested in applied science, and he becomes the CEO of the Philips company in Holland. And so what he states is comes from his own knowledge, and I let you read this sentence. I have heard statements that the role of academic research in innovation is slight. It is the most blatant piece of nonsense that it has been my fortune to stumble upon. I think there is hardly any example of 20th century innovation which is not indebted to basic scientific thought. And I think he wrote that in the 1940s, and during the second part of the 20th century and the beginning of the 21st, this sentence has been illustrated by many, many more examples, which I will be talking about. So let me start by making a very wide panorama of what science, driven by curiosity, has achieved over the last 3 centuries. We have had fundamental questions about light. Is light a wave, or is light a stream of particles? What is the velocity of light? Is it instantaneous, or does it propagate at a finite velocity? And many, many very bright people, not only physicists, but also philosophers, and all kinds of scientists have been interested in this question. I just show you here a few of these people: Newton, Huygens, Young, Fresnel, Fizeau have been working on this topic. Similarly, the same kind of similar question have been asked about the nature of matter. How does it carry electricity? What is magnetism? How does matter interact with light? And I show you a few people who have addressed these issues just on the basic science level: Coulomb, Faraday, Ampere, and of course Maxwell. And from this fundamental question, big discoveries have been made. And just to summarize, I can just briefly indicate what are generally the answers to these questions. Light, we know now that light is an electromagnetic wave which propagates at a speed which is independent of the observer, and that at the same time it is an ensemble of particles, which we call photons, which carry away energy and momentum. Similarly, the answer about matter can be summarized by saying that matter is made of atoms which combine positively charged nuclei with negative electrons, and that these electrons occupy discrete energy states, and they usually carry small magnetic moments. This knowledge has given rise to 2 theories which emerged at the beginning of the 20th century, telling us that light and matter obey strange laws which have very counterintuitive features. For example, in quantum physics, the notion of state superposition, the fact that the quantum system can be in different states at once before you measure it, the fact that 2 particles which are separated by a large distance remain linked by a kind of immaterial link which makes them just a single quantum system. If you do something of one of the particles, it has an immediate effect on the other. This is called entanglement. And all this is also subjected to the laws of relativity, which tell us that the time depends on the observer. And all this has come from basic science. The people who discovered that, all the people, the scientists you can see on this slide, never thought about the possible applications. And they just tried to answer fundamental questions they were curious about, and this has led to this kind of knowledge. I don't know what happens. So and of course they did not ask themselves what it would be useful for. But of course we know that all this has led to innovations which have changed our daily lives, which have allowed us to communicate faster and in a better way, which have allowed us to extract energy from nuclei in a way which was absolutely impossible to predict, to process information, to probe matter, to perform medical diagnosis, and so on. And this application has emerged often in a very unexpected way from the combination of several blue sky discoveries, and I will give you an example of that. So I would like to look at a few examples. I would first want to emphasize a great piece of useless research, which is the unification of electricity, magnetism, and optics, which was made by Maxwell at the end of the 19th century. What I show you here is the manuscript of the page in which Maxwell explained his discovery. In fact, what Maxwell did was, as you know, to combine the results, the discoveries of Ampère and Faraday about the interaction between electric and magnetic phenomena. What Ampère had shown is that an electric current gave rise to a magnetic field, and what Faraday has shown that the variation of a magnetic field produced an electric current in a loop, and they wrote equations to describe these effects. Maxwell took this equation, changed a little bit Ampère's equation, and found that the equation described the propagation of an electromagnetic field. The variation of the electric field gave rise to the magnetic field, and the variation of the magnetic field produced an electric field. And they propagate at a velocity which Maxwell's equation allowed him to compute. And he calculated them, and on this page, what he wrote at the bottom of the page is that he found that the velocity of this electromagnetic radiation was the same as the velocity that Fizeau and Foucault in France had measured a few years earlier, the velocity of light. And so I show you here the result of Maxwell calculation. He related the velocity. He showed that the velocity of the electromagnetic wave was 1 over the square root of the product of the electrostatic and magnetostatic constants, which had been stated by Coulomb and Ampère. And he compared that, and you can see it if you can read the page, to Foucault's measurement. And he said this cannot be a coincidence. The agreement of the results seems to show that light and magnetism are affections of the same substance, and that light is an electromagnetic perturbation propagating through the field according to electromagnetic laws. This is one of the most important sentences in science. It makes the first great big unification. It unifies electricity, magnetism, and optics in a theory which explains a lot of phenomena and predicts a lot of new phenomena. This is just blue sky science. And we know that this has had a lot of very interesting applications. For instance, what Maxwell has shown, that the light that we see, the light which is to which our eyes are sensitive, is just a very narrow spectrum in the range of all the electromagnetic radiations that should exist. So he predicted the existence of infrared and radio waves at longer wavelengths and the existence of UV, X-rays, and gamma rays at shorter wavelengths. And these predictions have been fulfilled. Hertz, 20 years after Maxwell, discovered radio waves, and nobody I think doubts the importance of these radio waves in today's technology. And 10 years later, Röntgen discovered X-rays. At the beginning, he called them X-rays because he did not know what it was, but it was discovered later that it was an electromagnetic radiation of very short wavelengths. And of course, this has led to a revolution in technology. Radio broadcasting, microwave applications, X-ray medical diagnosis, and so on. So this is, I think, the kind of illustration of the link between basic science and applied science that Flexner and Casimir did. But there is much more than that. Once you had these precise instruments and you started to study with more and more precision how light interacts with matter, puzzling question came, and this puzzling question led to quantum physics and to relativity. I cannot here discuss how this has come, but I would just say that it's by, for example, it's just by looking at the spectrum of the light emitted by heated bodies that Einstein realized that light had to be made not only considered not only as a wave, but also as an ensemble of particles, and this led to the notion of light particle matter-wave duality, which played an essential role for the birth of quantum physics. And also, another puzzling aspect of light was the fact that the velocity of light could not be combined with any other velocities. It was an absolute, a quantity which was the same for all observers moving at a constant speed with respect to each other, and this led to the principle of special and then general relativity with many, many applications. So you see that this historical panorama gives us already a good illustration of this link between basic science and application. But I would like now to focus on quantum physics. What I want to say is that when we, in the year 1900, when all these revolutionary ideas start to become discussed by physicists, quantum technologies were absolutely impossible to imagine. Lord Kelvin, for instance, in 1900 thought that the physics was almost completed and that there would be only obvious application of what we know at that time. The year 1900 was the year of a big world fair in Paris, and it was a time when the general public had a great trust in science and the progress that humanity will achieve using scientific knowledge. And so people have been asked to predict what would be the technology of the year 2000. And postcards have been published on that year, which would sound very naive now. You see here's a kind of prediction made about the telephone. So it was just, the telephone existed already at that time and it was nothing really new. People predict, radioactivity had just been discovered by the Marie and Pierre Curie. And you see here that they imagined that in the year 2000 we'll be heating ourselves in a fireplace by just putting our hands close to a piece of radioactive material. So it's not exactly what happened. And you see here the ways I thought mail would be distributed. Nobody thought about email at that time, just kind of extrapolation of a very primitive flying machines. So in fact, how did this quantum, so-called quantum revolution came about? I would like to, first of all, to show you here that all the instruments that we use in our daily life today come from this quantum revolution. Just a classical computer made of transistors would not have been possible if we didn't understand the way the electric current flows in conductors and semiconductors, how transistors work. The laser, which is an instrument which has revolutionized our way to communicate, for example, with the internet and optical fibers, would have been impossible without understanding the deep interaction between atoms and photons. The atomic clocks and the GPS is another illustration. Atomic clocks work on quantum principles, as I might discuss a little bit further later. The last example is MRI, magnetic resonance imaging. The fact that atoms have small magnets in their nuclei which process and emit radio frequency fields which can be detected and used to map the inside of complex systems is also a consequence of quantum knowledge. So how all this did come about? And I will now try to make a brief history of the experimental discoveries which have led to these applications. So we start with a blue sky discovery made by a German physicist Otto Stern in 1922. Otto Stern wanted to measure the magnetic moment of atoms. It was known since Ampere that the magnetization of matter was certainly due to the fact that there were small electric currents, loops of electric currents in atoms which produce magnetic moments. But these had not been measured. What Stern did was to have a furnace from which he evaporated a beam of silver atom in vacuum, and he applied a gradient of magnetic field, assuming that this magnetic field will deflect the atoms according to the size of the magnetic moment. And what he expected to find on the detector that you can see on the left part of the screen, he expected to see a trace, a continuous trace, corresponding to the distribution of all possible orientation of the magnetic moment with respect to the magnetic field gradient. And what he saw instead, at his great surprise, that he only saw two spots, which is the first indication that, in fact, what happens? Correct. The setup separates, in fact, the magnetic moments, pointing up and down, and it shows what is called spatial quantization. The magnetic moment cannot take a continuous value on a given axis. It can only point up or down. This is what we call now spin up or spin down. And you see on the left part the trace that Stern observed. In fact, the separation is large at the center, and then it decreases on the edge because the magnetic field decreases on the edge. So what is important is that this double lip, which shows this quantization. And what I claim is that this single split trace heralds the 20th century quantum revolution in technology, because from this experiment, all has started. Otto Stern had a graduate student, Isidore Rabi, was an American who came from New York to Germany in the 1920s to learn about this technique of atomic beams and to export it to the United States and to try to do interesting experiments with it. So you see here a picture of Rabi, and the kind of experiment Rabi did is shown at the bottom of the slide. In fact, what Rabi did was to generalize Stern method to make the experiment a little bit more subtle. And so you see that his atomic beam now has three zones. In zone A and B, a gradient of field is applied in opposite direction, which means that a magnetic moment would be deflected upwards in the first zone and then in the opposite direction in the second one. So the atoms will undergo a kind of S shape, and they will be focused on a detector, just a hot wire, on which the atoms will be deposited, eject electrons, and electric current proportional to the flux of atoms will be detected. Now, the great invention of Rabi was to put a third zone in between, what I call the zone C, and in C, a radio frequency field was applied in order to switch the spins from up to down. So you see that, in fact, the quantization means that you have two possible values of the energy in the magnetic field, spin up, which has a positive energy, spin down, a smaller energy. And if radio frequency field of the right frequency hit the atoms, the spin will go from up to down. But if the spin flips, when the atom reaches the second zone, they will no longer be focused on the detector because the spin will have the wrong direction. So what he expected, what he saw on the detector is that when the frequency was right, the signal decreased, and that this is called a magnetic resonance. The signal depends upon the value of the frequency with respect to the size of the magnetic field, and by finding what was the frequency which made the spin flip, he was able to measure the value of the magnetic moment of various nuclei. So it was just a blue sky basic science experiment to understand what is the size of the magnetism contained inside the atoms. But this, he immediately understood that this might have applications. And in fact, this discovery opened the way to magnetic resonance imaging, to atomic clocks, to the laser, to the GPS system. In 1939, Rabi went to a meeting somewhere in the United States, in Columbus, Ohio, and he gave a talk, and so there were some journalists who attended his talk, and you see the headlines of the paper which was published after that. We are all radio stations, Columbia scientists, so Rabi reports, all atoms in humans or in steel found to emit and receive long-wave radiation. So what the journalist said that Rabi had said, I don't think there is a record of his speech, but Rabi said, the same kind of magnetic moments which exist in my beam, my molecular beams, should be there inside our bodies, and should, when the atoms, the spin flips, they should emit radio waves. And so we are radio wave emitters. And this was a premonition of MRI. It's exactly what MRI is doing. Magnetic resonance imaging is detecting these radio waves to provide information about what's taking place inside ourselves. But in order to be able to detect this radiation, other progress had to be made. And the next big discovery was made by Felix Bloch and Ed Purcell in 1945. What they discovered is that you don't need an atomic beam. You can interrogate directly the atoms and the molecule inside a solid or a liquid. And this was a great discovery of nuclear magnetic resonance. I show you here the setup. You have a sample which contains the system that you want to study. You have a coil which allow you to send radio waves, and you need, of course, a radio wave emitter. And then you have a second set of coil which detects the flipping of the spin, the radio waves which are emitted by the resonantly excited nuclei. And when you scan the frequency of your emitter, you get lines which give you an indication of the nature of the elements that you have in your sample and also the perturbing environment. If you have electrical and magnetic field in the sample, they will move, they will make this line move or broaden, and you have a wealth of information that you can get from this thing. So this is a blue sky discovery, of course, but it had made it possible by technological advances. In fact, the radio wave emitters, which was used by Purcell and Bloch, are exactly the same which had been developed during the Second World War to build radars. So in fact, this is a kind of blue sky discovery which was made possible by technology. So you see, it doesn't go one way. It's not only basic science which produces technology. Technology also allows you to discover, to make basic science discoveries. And of course, all this has led to very important applications. In fact, I want to show you on the next slide the beginning of the Nobel lecture, which was given by Ed Purcell when he received the Nobel Prize for NMR in 1952. He said, so Professor Bloch has told you how one can detect the position of the magnetic nuclei in a drop of water. And he went on to say what I have underlined. I remember in the winter of our first experiments, just 7 years ago, that is in 1945, looking on snow with new eyes. There's a snow layer on my doorstep, great heaps of protons quietly processing in the Earth's magnetic field. To see the world for a moment as something rich and strange is a private reward of many a discoverer. This is typically a blue sky sentence. It does not say that he discovered something which will be useful. It just says that he proved the kind of joy and emotion he felt because he knew something that nobody else knew at that time. And then, of course, he went on to say, what can we learn from all this about the structure of matter? And this has led to all the applications. So, of course, magnetic resonance imaging is the one I would like to briefly evoke here. We have in our bodies a lot of water molecules. In the water molecules, you have hydrogen atoms. Hydrogen, on the proton of hydrogen have magnetic moments. These moments precess in magnetic fields, and so this is the basis of an MRI. You need to have a large magnetic field to get precision in the measurement, and for that you have to insert the patients into a big coil, which has to be cooled at liquid helium temperature, because this coil carries superconducting a current which is sustained in a superconducting material which requires very low temperature. And you need, of course, also computers to transform the signals that you detect into interpretable signals. So these are, I think, at least 3 quantum technologies: magnetic resonance, superconductivity, and computers, transistors and computers. And this has led, of course, to the revolution of MRI, and in particular to MRI of the brain. So you see here a picture which shows when you ask someone, a patient, to think about something, there are some part of his brain in which the magnetic resonance signal changes. This is called functional MRI. When some parts of the brain have become active, the blood flux in this part of the brain is increased. Since the blood contains hemoglobin molecules which carry magnetic moments, this modifies the magnetic environment, and this gives rise to an observable signal. So, and this is something that, of course, Purcell could not dream about, and it came 30 years after Purcell's discovery. So let's go to another direct application of Rabi atomic beam machine, the atomic clock, which operates on an improved Rabi machine. In fact, Ramsey had improved the precision of the atomic beam resonance method by having the atom cross not one radio frequency zone, but 2 separated, specially separated zones, and this is known as the Ramsey separated zone method. If you do that, what you observe as a resonance is not a single resonance, but you have fringes. You have a resonance signal which have very narrow features, and this is a quantum interference effect. It comes from the fact that when the atoms have crossed the 2 zones, you cannot know whether the spin flipped in the first zone or in the second zone, and you have a quantum interference. You have a probability amplitude for the spin to have flipped in the first zone, a probability amplitude for the spin to have split in the second zone, and when you add these 2 amplitudes and compute the total probability, you find interferences with very narrow features. And by locking the microwave to be on the top of the central fringe, you have a very precise way to control the frequency of the microwave, and this gave rise to very precise clocks. In fact, the clocks is just counting the frequency of a microwave which has been locked to the cesium atomic transition. This is a big difference with previous clocks. Previous clocks were all based on a man-made system, either a pendulum or a quartz, something whose exact frequency depends upon the way it has been fabricated. Here, the time is measured from a fundamental property of an atom, and the cesium atoms are the same all over the universe, on the Earth and everywhere else. So an atomic clock which is based on that is much more precise and much more reliable than a previous clock. And this had led to a huge jump in the precision. Here, this kind of atomic clocks have an accuracy of 10 minus 14, which means that they deviate from each other by no more than 1 second in a million years. And these are the clocks which are typically used in the GPS system. Clocks are embarked on the satellites. They send signals to your cell phone, and from these signals, by triangulation, you find where you are on the surface of the Earth with a precision of a couple of meters. In order to have these clocks working, you have to be aware of the fact that the clocks which are in the satellites click at a different rate as the one you have on Earth because of special relativity and because of general relativity. If these corrections are not made, the GPS system is off by several kilometers and completely useless. So again, you have basic science, quantum physics, special and general relativity, which have led to something very practical that we all use today, most of the time without marveling about that and without considering that this comes from basic science. That's good. I have something which doesn't work on the computer, but that forced me to slow down. So. Now, the last direct consequence of Rabi's kind of experiment is the discovery of the laser. The notion of stimulated emission of light was discovered by Einstein in 1916. What Einstein found is that if an atom is excited, one knew before that if an atom is excited, it goes down to the ground state by emitting a photon. This photon is emitted in a random direction with a random polarization, a random frequency. But if you send already some light on the excited atom, it will have a tendency to emit the photon in the same mode as the one that it has received. As opposite to spontaneous emission, this is called stimulated emission. This is an amplifying process which tends to increase the light emitted in a given mode, and this expresses the tendencies of photons to, the gregarious tendency of photons to really to go in the same mode. This is a bosonic property if you want to use language of theoretical physics. So you see here the absorption process. Atoms goes from the ground state to an excited state, and the opposite process is spontaneous emission, but on top of spontaneous emission, you have also stimulated emission. An excited atom receiving one photon emits another photon in the same mode with the same phase, the same frequency. This process is an amplifying process, and it has led to the discovery of the laser. If you put this amplifying media between mirrors, and if you excite the atom in the upper state, the noise spontaneous emission noise will be amplified preferentially in the direction in which it can build up between two mirrors. And if one of the mirrors is slightly transparent, you will have a beam of coherent light emerging from this mirror, and this is the laser light. But at the time of Einstein, it was impossible to build the kind of cavities, to find the way to prepare the atom in the excited state. It took something like 50 years before the laser was invented. On this slide, I just trying to show in a very schematic way the difference between ordinary light and laser light. In ordinary light, each atom emits a photon in the source, emits a photon independently from the other. So the photons have different directions, slightly different frequencies, different phases. So this is what I would call natural light. In the laser, all the photons are in step. They're all in the same direction, all with the same phase and the same frequency, and this gives rise to very peculiar properties of laser light. And this was the first device in which this kind of emission was found is a maser, that is a system which emits in the microwave domain. Maser is an acronym for microwave amplifier by stimulated emission of radiation, and the device that you can see here which is shown by Towns and his student Gordon, is an atomic beam machine, a molecular beam machine, the same kind of machine that Rabi and Ramsey had used. And the amplifying medium was an ammonia molecule. The system has been then extended in the optical domain. The M of maser has been replaced by the L of laser, light amplification by emission of radiation, and this has led to the laser, which is a fantastic source of light. And on this slide, I just summarize mainly its properties. It's a beam which can have a huge intensity. It can be used to fuse and evaporate matter, reach extremely high temperatures, and paradoxically, it can also be used to slow down atoms by having atom absorbing the momentum of a light beam going in the opposite direction, and to reach the lowest temperature ever achieved, temperature of the order of 1 billionth or even less than 1 billionth of a degree. And at this low temperature, new forms of matter appear, Bose-Einstein condensate, Fermi-degenerate gases, which have quantum properties which were impossible to study before. Another set of interesting properties of the laser is that these beams have ultra-stable frequencies and phase, and they can be used in interferometric devices to achieve huge precision in the measurement of distances. It is by having this kind of laser light in a Michelson interferometer that the first gravitational waves have been detected 6 or 7 years ago. You can also combine this very stable laser to build up by interference extremely short pulses of light, like bullets of radiation, which have a duration of attoseconds, a few tenths minus 18 seconds, which allow you to probe and to explore very fast phenomena in atom molecules and condensed matter. So it's a very flexible tool for fundamental research in physics, in chemistry, in biology, and for applications to meteorology, to medicine, to communication. And just because I have spoken a lot, I would just very briefly summarize what is happening now. Now, using laser light, you can manipulate single atoms. You can put them in a well-defined configuration. You see here, these 5 bright spots are 5 beryllium ions which are held in an ion trap. The ions can be addressed individually by laser light and can be used as quantum bits of information that you can manipulate and detect. You see further, this was about 20 years ago. Now you have streams. You can control streams of ions. Here you have up to 50 ions, but now you can do that with a few hundred ions that you can control individually. And this is, of course, a starting point to try to build a quantum computer. And what we are doing in Paris is to trap photons in a cavity which can keep the photon for a very long time and send atoms one by one through this cavity and study the coupling, the quantum coupling of the atom with the cavity, with the photons inside the cavity, to study non-classical states of light. Just show you briefly here the kind of map that you can make of a quantum field by doing these experiments. Here you see what is called a Wigner function. It's a kind of radiographic picture of the field in the cavity. The 2 Gaussian peaks that you see represent a field which associates with one phase or the opposite phase. And in between, you see fast fringes, which are a signature of the quantum coherence, of the fact that we are in a quantum superposition of these 2 states. We call that a Schrödinger cat of light. It's a light field which is trapped in the cavity and which has at the same time 2 opposite phases. This quantumness disappears very quickly due to decoherence, and by using these methods, by interrogating these atoms with these photons with atoms, we're able to study how decoherence very quickly erases the quantumness to bring us back to a classical world in which the cat has to be dead or alive, both at the same time, dead and alive. So I think it's time to conclude. What will we do? What could we do with this by exploiting the fact that we can now prepare and control superposition and entanglement? Some people like to call it the second quantum revolution. The first being the one I discussed before, the fact that you use the bulk properties of condensed matter system and of light to bulk properties which are quantum phenomena to build classical devices like the GPS, the atomic clocks, and so on. Here we are going one step further. We want to use directly the quantum strangeness to achieve new things. We can talk about quantum metrology, which is to use the fragile features of quantum state to measure small effects with more sensitivity than by classical means. And a good example are atomic clocks. Now the atomic clocks are 100,000 times more precise than the one used for the GPS, just because that instead of measuring microwave frequencies, they are able to measure directly optical frequencies, and a lot of application can be expected from that. The second point I would like to emphasize is quantum communication. You can use entanglement. You can prepare entangled pairs of photons, propagate them over large distances, for example, in optical fibers, and use entanglement to communicate in a way which cannot be spied upon. This is called quantum cryptography. You can think also of quantum simulation. That is, you can manipulate atoms one by one to prepare configuration of atoms in a lattice and have these atoms simulate what happens in real matter, but at much different scale, and try to build up artificial matter which will exhibit properties that you don't have ordinarily, that you don't know how to produce in condensed matter. For example, can we find a way to prepare a superconducting material at room temperature using this kind of ideas? And the last point, but not the least, is the famous quantum computer, which would make use of this quantum logic to achieve calculations that a classical computer cannot. But in this case, you would have to tame Schrödinger's cat in a very efficient way, because what a quantum computer would be, it would be a cat with a huge number of particles interacting and evolving without any decoherence, and this is something we don't know how to do now. So all this research is being done very actively in the world. I think a lot of things will happen. Most of them, I think, not predictable. So I have, in conclusion, here I just emphasize one of the latest developments is the new development in atomic clocks. They work now at 429 terahertz. Terahertz is 10 to the 12, so it's 10 to the 14 hertz. That's 14 orders of magnitude higher than the pendulum clock, which started the scientific revolution in the 17th century. So we have won 14 to 15 orders of magnitude in the precision with which we measure time. And this increase in precision has accompanied and triggered all the revolutions that I've been talking to you about. The uncertainty is now such that two clocks which would have been started at the beginning of our universe would not deviate from each other by more than 1/20th of a second. These clocks are 100,000 times more precise than the GPS clock. Due to the curvature of space-time predicted by general relativity, the time does not elapse at the same rate depending upon the strength of the gravity fields we are in, which means that in this room, if you move up and down, a clock does not give you the same time. Now, this was known for at least 50 years, having clocks at different heights differing by kilometers between Earth and satellite, by hundreds of meters, tens of meters in Harvard, by a famous experiment made by Ripka and Pound in the 1960s. Now, with these clocks, you see the difference when the difference in altitude is 1 millimeter. So it's a very stringent proof of general relativity. And it also, so this is illustrated by this famous kind of paintings by Salvador Dali. It means that the time measured by the clock is no longer the same at the top and the bottom of the same clock, because the clock is more than 1 millimeter in size. So it gives a new definition of time, and it opens the way to a lot of applications. So to conclude, I show you on this slide the two-way connection between blue sky research and innovation. You start by observing nature, you build theoretical models, This leads to the prediction of new effects, and this leads to novel technologies. But these novel technologies, for example, the lasers, the atomic clocks, allows you to do more precise observation, which either confirm or falsify the theory you have started from. So it's a loop. It's a kind of virtuous loop, which is a loop of science, which connect basic and applied science. Now, what will happen in the future? I think if you have followed what I said about the postcards of 1900, we have to be very careful about what we say. What will the second quantum revolution bring us? Will it be quantum computers, quantum communication, quantum meters, or something else quite different? We don't know. But what is sure is that without basic research, nothing will happen. And the past teaches us that wonderful applications often emerge in an unexpected way from blue sky research. So I have finished. I just want to conclude, to come back to Abraham Flexner. Flexner explained all that, but he said something else which I think is very important. He said that beyond its usefulness, basic knowledge is an essential pursuit of mankind, and it is especially necessary to preserve the values of civilization in dark and dangerous times. Flexner wrote this, and the sentence that I will show you, in 1939, just before the Second World War. And he said this, which we have to reflect upon today. Is it not a curious fact that in a world steeped in irrational hatred which threatens civilization itself, men and women, old and young, detach themselves wholly or partly from the angry current of daily life to devote themselves to the cultivation of beauty, to the extension of knowledge, to the cure of disease, to the amelioration of suffering, just as though fanatics were not simultaneously engaged in spreading pain, ugliness, and suffering. And I think this is a sentence which resonates today, and which is as valid as it was in the 1930s. I think by doing science, we contribute to maintain humanity in the world. Thank you very much.
Well, thank you. I think that the message was very clear. Hello, I'm Jenny Hernandez. I'm the Vice Dean of Research of the School of Sciences, and Cesar Galindo, the Academic Vice Dean of the School of Sciences. We are going to ask a couple of questions. We don't have that much time because the auditorium is booked for other event, but I will talk, but we'll be fast to see if we can take one or two questions from the audience. And so I don't know, if Cesar, if you'd like to start.
Well, thank you very much for the very nice talk. Yeah, I am a mathematician, as I told you, and when the title, I as a mathematician look very reflected in the sense that, I don't know, even my mathematical heroes of the past, like Gauss or these kind of very big names, they at some moment start to, I don't know, study arithmetic of modular arithmetic just by curiosity, and even in some moment they said things like, this won't have any application, but it's beautiful and it's just by curiosity. But of course, they didn't have the opportunity to know that, for example, nowadays RSA is based on modular arithmetic. And later, another mathematician like Peter Shor, related with quantum computation, he realized that it's possible in principle, if there is this kind of machines to factorize numbers and then to break, and all these things seems at the beginning, let's say, useless knowledge, but later it has a lot of things. But in both cases, they are quite related in some sense with interdisciplinary, because they were people that were thinking in different areas and to thinking what is perhaps the role that interdisciplinary research can play also in this virtual circle that you show us. In some moment, technology seems to play an important role, that later basic science, but this is not to be done only for one kind of scientist.
First of all, thank you for bringing back the question of mathematics. And this is part of what I wanted to say. Mathematics, as you said, seem to be completely useless. And one of the wonders of science is that mathematics is useful to understand the world, that physics is based on equations, on mathematics, and that theories which were born in the mind of mathematicians have been proved useful later on in physics. One example is Évariste Galois group theory, which is the basis of understanding the symmetries in quantum physics. Another example, much simpler, is the discovery of complex numbers, which is essential to discuss electromagnetic field and the relationship between phase and amplitude in this kind of phenomena. Another example is non-Euclidean geometry developed by Riemann that Einstein used in his general theory of relativity. I think it's really amazing that the world is mathematics and that mathematics is really emerged from human brains to be later on useful in science. Now, you talked about interdisciplinarity. It's clear that this loop works not only in physics but in other fields, and that I gave an example, the fact that physics has allowed to develop MRI. It is a tool for biology and neurosciences. NMR is also useful in biology. In fact, there is a field of NMR which allows to study how the configuration of protein changes under various processes, and you can measure the folding of proteins by exploiting NMR signals. So if you want to progress in science, you have to be able to see this connection and try to find where the interdisciplinarity would allow you to achieve things which are not possible if you confine yourself in only one subfield.
Thank you. I have a question regarding, measuring things so precisely. As experimentalists, we know that it is very difficult, but that has an effect on people's lives directly. So maybe when you talk about quantum metrology and the importance of metrology, and for a country to have a good metrology office, so having kind of the sense of the importance of having precise measurements, especially time. So maybe if you can comment on that.
I don't know what will already be useful in the future, but it has been speculated, for instance, that atomic clocks, which are as precise as the one I discussed at the end, could be used to warn us about earthquakes, because before an earthquake occurs, there are slight changes in the distribution of masses inside the Earth, and these produce very slight changes in the gravitational field. And if these clocks are sensitive enough, they might be able to give a warning before the earthquake happens. So, and it's a signal which is of a nature different from the seismograph. So this is one possibility if you want to use that. Now, you can also think that if you have probes which can measure magnetic fields at a very short distance, it could be used to study biological processes, what happen, the change in magnetic fields inside or at the membrane of cells. and it can have biological application, but I don't know this field at all. So it's very difficult to predict what will really be useful, but you can certainly see the link which may lead to application. In the case of metrology, I think this is one possibility.
Okay. Thank you very much. So maybe we have time to take one question from the audience. So I don't know if there's like microphones. There's a question there. There's a microphone coming.
Thanks a lot for your presentation. What kind of experiences you highlight in your life to obtain your Nobel Prize? Thank you.
What?
What kind of experiences in your life you highlight to obtain your Nobel Prize?
What are the experiments which were?
No, experiences
in
your
general.
life.
Has been the Nobel Prize? Very, very big experience. I think it has, the Nobel Prize exposes to a lot of attention from the media, and you are asked to intervene not only like I do here in a lot of academics, but also in high schools in front of students, and also in forums in which politicians and economists meet with scientists. And so I think our duty is to try to be an advocate for science and try to make the ideas that we discussed today become more obvious for the general public and for the government politicians. The fact that you need science, of course, for social application, but you also need science as a part of culture. And so I try to do that, and I try also to avoid answering to questions which have nothing to do with science and for which I am not particularly an expert in. And so it's clear that the Nobel Prize exposes you to a lot of events of this kind. I enjoy when I think it can be positive and useful. This is, I think, what happens today. The problem I see is that usually when I talk to a selected audience, everybody agrees. So it's not this, I'm sure I don't have to convince you of the importance and the beauty of science, but and the people who are questioning science, the people who are suspicious about science are the ones which should be convinced. But I don't think this can be done at this level. This can be done only at a much deeper level by improving the general education. And this is also one thing I try to discuss and to promote, the fact that education at an elementary level and then throughout the studies going through middle school and high school has to be improved, and particularly improved in mathematics and in science in general, so that the critical judgment, the rational thinking, which is essential for science, be a common knowledge, and we are far from that, and I think we have to fight in that direction.
Well, I think with that, but thank you very much for your talk and for your presence at the University of Alexandria. Muchas gracias a todos por haber asistido. Realmente estamos muy contentos de haber realizado este evento con la Facultad de Ciencias, el iFestival y el Centro Cultural de Uniandes. Entonces, los esperamos en próximos eventos. Muchas gracias.
Le solicitamos al público asistente no descuidar sus objetos personales.